folks, for our last topic in this massive chapter 16, we're going to be talking about solubility equilibria. So this is going to be applying our concepts of equilibrium to understanding how certain ionic solids precipitate and form insoluble solids under certain conditions. Okay. And so we think of that as an equilibrium reaction. So for example, here is a calcium fluoride solid. If we recall from our solubility rules, we would find that calcium fluoride is insoluble or slightly soluble. And so what that means is if we have some amount of calcium and fluorine present, we expect a precipitate to occur. Okay. But now we can put some quantitative numbers on that. We expect a precipitate to occur only when there's a certain concentration of calcium and fluoride. Okay. So for example, if we think of this as the solid dissolving into the two ions, then because this is equilibria, we recognize the two ions could reform the solid. Okay. And so when equilibrium is reached, we say the solution is saturated. So that means it can't hold any more ions. So if we had this equilibrium, and the equilibrium of this solubility is given by, let's say if we have some test tube and we've got some solid precipitate, okay, so there's our precipitate. And then, of course, we have a supernatant above the precipitate. That supernatant will be saturated in ions. So if we put any more ions in there, they will precipitate and make more solid. So our solution will be saturated. It can't hold any more ions. So we write this equilibria expression with the solid as the reactant, and here it's in equilibrium with its ions. And so now we're going to add another flavor of K, KSP, which is solubility product. If you recall, we don't include solids in the equilibrium expression, so our equilibrium expression is only comprised of these ions. Okay. And so what will happen now is the concentration inside these brackets are what we call the solubility. Okay, so I'll say that gives us the solubility concentration in molarity, which is to say that's the maximum number of ions we can hold in solution. All right. So here I've got a whole bunch of KSP values and various solids listed. And what you'll notice about all these KSP values, they're all really tiny. I mean, look at this. Copper 2 sulfide, 10 to the minus 36. That's crazy. Or even lead 2 sulfide, 10 to the minus 29. So this means the equilibrium position is strongly on the left. So that means we don't expect these solids to dissolve very much. Another way we can think of it is we expect these molar solubilities to be quite small because if this KSP value is small, then we know that the equilibrium position is way to the left. So we're not going to see a whole lot of these ions dissolve. Okay, so let's do some example problems. Okay, so the KSP value for copper 2 iodate, and there we have the formula, is 1.4 times 10 minus 7 at room temperature. Calculated solubility in molarity. Okay, so let's write that reaction down. So we write this down as the solid dissolving, okay? And it dissolves to form, so we recognize that's got to be copper 2 plus, because here the name, it said copper 2. Okay, and then now we also recognize that we have 2 iodates. That's 2 IO3 minus. Okay, So now we could approach this in the same way that we've done before by using a rice table. However, what we would recognize is our rice table for this is always going to be really simple because we're not ever going to have anything for this solid, at least not in our rice table, because we don't include solids in the equilibrium expression. So now what I'm going to do instead, I'm going to put a letter S right here, where that letter S means my molar solubility. And before we had used the letter X, so no different really, we're just changing the letter. Okay. So now if this I'm going to call S, this has got to be 2S, right? And then now my KSP expression would be KSP equals, and it's going to be S for copper times, and now we have to remember to do this whole double jeopardy thing, right? Where we recognize the molar solubility of iodate is 2S, but in the equilibrium expression, we know that we have to square that. So that's all going to become S times 2S all squared, which is going to give me 4S cubed. And once again, S is my molar solubility. So now all I have to do is rearrange this equation and solve for S. So I'll go ahead and do that now. So I'm going to divide both sides by 4. Okay, so that would be KSP divided by 4. And then now because S is taken to the third power, I want to take both sides to the 1/3 power. So that will leave me with just S, and now this becomes to the 1/3. And so now my KSP is going to be 1.4 times 10 minus 7 all over 4, and now to the 1/3 power. And that will, as you can see, quite simply give me my molar solubility. So let's do that in the calculator. 1.4 E minus 7. And now we'll say divided by 4 equals. And then now there's a couple ways I can do it. On this calculator, I can say this button and push the 3, which would be the same as taking this to the 1/3 power. Okay. And to 2 significant digits, I get 0.0033. And that's going to be in molarity. So that is my molarity of copper 2 iodate. And so what that means is I can dissolve as much as 0.033 moles per liter of copper 2 iodate and not get any precipitation. If I go just barely past this number, okay, then I will get a precipitate. And any amount of copper and iodate that I add past this amount will strictly lead to precipitation and not more ions in solution. Okay. And then now if we think about these ratios, okay, so this is telling me that if I had a solution that was 0.033 molar in copper, and if I had a solution that was 0.0066 molar, so 2 times that value, that would be my threshold amount of those 2 ions before precipitation would occur. Okay. So let's do now another type of calculation. So bismuth sulfide, and there it is, has a measured solubility of 1.0 times 10 minus 15 molar. Calculate its KSP value. Okay, so now that's kind of thinking of this in the other way. And so let's write up that reaction. Bismuth sulfide, okay. And we're going to always take our time to write out these reactions so we get the number of ions right. So here we can see that sulfide is always 2 minus, and there's 3 of them. So that means this is 6 minus. So that bismuth has to be 3 plus, okay? Make sure you're good at working out your formulas and all of these stoichiometric ratios, okay? And so now that means we need 3 sulfides that are 2 minus, okay? And if I do the same thing now, if I invoke this letter S, what I'm going to actually see is I need to call this one 2s, and I need to call this one 3s. And so now because really that means that my solubility of this entire compound is just 1s, which is the same as what it was here, all right? Because of that 1-to-1 ratio. So now if I'm setting this up, KSP, so that's going to be 2s all squared times 3s all cubed. And so what we have now is 2 squared times 3 cubed. So let's put that together. So 2 squared, of course, is 4 times 3 cubed. And that whole thing now equals 108s to the 5th power. I was given the value of S, that molar solubility. Now I'm asked to calculate KSP. So that's just simply going to be 108 times, and now I put in that molar solubility, 1 times 10 minus 15, all to the 5th power. And you can see this is going to give me a crazy small value of KSP, which is to say bismuth sulfide forms a solid when you look at it funny. So it does not want to exist as ions. It wants to exist as a solid. So I'm taking 1 times 10 to the 15th to the 5th power times 108. And so with 2 sig figs, I get that to be 1.1 times 10 to the minus 73, which I know is like so small it seems ridiculous. But this is one of the only times in this class that we'll see crazy, ridiculously small numbers like that. Okay, I'm going to record a part B for some more sample calculations.